In this video, I'm going to be discussing infinity as we treat it in AP Calculus. Okay, so I'll be talking about, limits as x goes to infinity. I'll also be talking about limits that when we consider them, they come back infinity or negative infinity. And how are we going to talk about that? Okay, because, just in the most basic sense, I'm going to just talk to you about the graph of y equals 1 over x. And actually, I'm only going to draw a picture of this for you in the first quadrant, right? Because we're pretty solid on what the graph of 1 over x looks like, right? It's going to start off really big, and then it's going to get really small, okay? And we know, maybe just to make it look a little better, I'll say that this is 1, and that's 1. Okay, so then 2 would be a half. Okay, and then now I can get a really good, sketch of the graph of y equals 1 over x. Maybe I should have been using graph paper for my lessons this whole time. But anyway, okay. Now I've got two things that I can see are happening. That the closer x gets to 0, the closer 1 over x is getting to infinity. So this is, the graph of f of x equals 1 over x. Okay. Now, I'm not going to actually write this in a limit notation. I'm just going to kind of show you what I'm talking about. So I'm going to say, as x approaches 0, now I know that I need to be a little more specific. As we're approaching 0 from the positive side, 1 over x is getting really big. We can make 1 over x as big as we want by just choosing a small enough value of x. If you want me to make it bigger than 10, I just need to choose x less than 1/10. If you want me to make it bigger than 500, I need to choose x less than 1 over 500. We can make this as big as we want just by choosing sufficiently small values of x. So that's what it means when we say it goes to infinity, is that we can make it as big as we want. Infinity is not a real number. 1 over x will never equal infinity. Nothing will ever equal infinity, right? But we can say that it's going towards infinity. And then over here, we've got a very clear behavior, and we know about what happens to 1 over x as x gets bigger and bigger and bigger, right? We know that if we have one pizza and there's 3 of us splitting it, okay, we're each going to get a bunch of pizza. But if I take one pizza and I try to divide it amongst every student at Lake Travis, every person can get like a tiny little, little dot of pizza, okay? And if I try to divide one pizza up against, everybody in Lakeway, then, everybody gets pretty much nothing. And the more people I add, the less pizza we all get. So as x approaches infinity, 1 over x is going towards 0. And just another thing I need to point out, that this does follow those rules that you had in pre-cal and algebra 2, where if it was heavier on bottom, as time went on, the fraction went to 0. Okay? And that's basically why. It's because you're dividing by more than 1. Okay, so let's actually get into what do we actually mean when we consider the limit as x goes to infinity. Okay, so I'm just going to start with the statement that the limit as x approaches infinity of f of x is equal, that there is some limit of the function as x goes to infinity. What this means is that for bigger and bigger values of x, past some point, the bigger I make x, the closer I get to L. Or, the actual definition of the limit as x goes to infinity is that I can make my f of x values as close to L as I like by choosing sufficiently large values of x. Now that, as large as you like, sufficiently large, in the independent variable, that's an analysis level description of the limit. Okay, and this is not an analysis course. So what I'm going to say is, when you think about this, you're going to say that there is a horizontal asymptote. Okay, and it is possible for a function to have more than one horizontal asymptote. Okay, y'all already are familiar with a function that does have 2 horizontal asymptotes. You just may not have considered the graph of it, especially last year. Okay, and that would be arctangent. Okay, So that's really what I'm just asking you to think, is that the limit as x goes to infinity, we're going to be considering horizontal asymptotes in the same way that we did in pre-Cal Algebra 2. We're going to be thinking, is it heavier on top, heavier on bottom, essentially the same on top and bottom, and we'll have ways to deal with all that. And I'll have a lot of examples going forward. Okay, but just real quick, something I'm going to point out to you is going to be the function arctangent. Okay, so let's talk about f of x equals arctangent of x. Okay, so the graph of this thing, and I am assuming you're pretty familiar with arctangent, but draw you a quick little picture. And we know that arctangent of 0 is 0, and so I'm not going to really try too hard to make this like a perfect, beautiful graph, but I think I am going to, I know what I want to make the horizontal asymptotes to in scale. Okay, and it has a different horizontal asymptote as we approach positive infinity and negative infinity, and that is entirely possible. We'll see other functions today that are going to do that. Okay, and it has to do with the unit circle, right? And, you know, normally at this point I would be like, all right, does anybody know what the equation of this horizontal asymptote is? And I would wait, and, you know, usually one person will figure it out. But I want you to think, you can't plug in infinity into arctangent. But tangent can get really big, right? This is kind of like the graph of tangent turned on its side and maybe reflected a little bit. But on the unit circle, we're talking about the arc whose tangent is going towards infinity. Okay, arc meaning like angle. So I'm going to just draw my little unit circle, and I know where tangent is undefined because of division by 0, which is basically, you know, what causes infinity type situations. It's up here, right? This is where it goes to positive infinity, because tangent starts off at 0, at pi over 4 it's 1, but then it keeps increasing because of the way it's just got that arm that just keeps going up towards a vertical asymptote. Well, the closer I get to pi over 2, remember tangent's y over x, the y coordinate on the unit circle divided by the x coordinate on the unit circle. And on the unit circle, this is the point where x is equal to 0. So I'm getting close to dividing by 0, which means I'm getting really big. Okay, meaning that the arc that's going to cause that infinity is going to be pi over 2. So this is the horizontal asymptote that's y equals pi over 2. And maybe you just guess from the symmetry of the graph that this is going to be negative pi over 2, and I mean, you'd be right. But and the reason why is that as we go towards negative pi over 2, well, I'm getting closer and closer to y is negative and x is positive, meaning that the tangent is definitely going to be negative. So our tangent of negative infinity, when is tangent coming back negative infinity? Well, never. But it's coming really close to coming back negative infinity right there. Okay, so that's a function with 2 horizontal asymptotes. And I will show you a couple more before the end of this video. All right, so real quick, I'm going to give you some guidelines on really reminding you of what you already know about horizontal asymptotes. And this is presuming that you're kind of looking at something algebraically and you have a fraction and we are considering what happens as the independent variable goes to infinity. Okay, if it's heavier on bottom, we're dividing by more and more and more as time goes on, and it's going to 0. And heavier on bottom could be, I'll give you kind of the taxonomy down here in a second of, you know, relative growth rates. Heavier and less heavy, but heavier on the bottom is going to go to 0, which could be, you know, something like 1 over x, or 2x minus 5 divided by, you know, x to the 14th power. That's going to be much heavier on bottom. Or something like x to the 9 divided by e to the x. E to the x is heavier than any polynomial for reasons that we will see throughout this course, and that would go to 0 as well. And I'll show you about that and give you kind of like a running list of biggest to smallest. And if heavier on top, there is no horizontal asymptote. Okay, but saying that the limit doesn't exist isn't always sufficient in this class. So I'm going to say it's either going to go towards infinity or it goes towards negative infinity. And I'll show you more about what we mean when we say that later. I'm going to talk about when the limit equals infinity. Right now I'm really focused on the limit as x goes to infinity, but when the limit comes back infinity, well, I'll talk about that at the end of this video. And essentially are the same. You usually say e's for exponents are the same, but we aren't always going to look at just polynomial on top, polynomial on bottom. We could have polynomial exponential, we could have log polynomial, something like that. If they essentially are the same, that's when we're going to divide coefficients. I don't even say lead coefficients, it's the coefficients of the things that are the same and at the largest power. So I'm just going to say divide coefficients. Okay, really assuming that you've done this before. So here I'm going to give you, okay, so really we've got first our polynomials, right? That's what we're used to. The nth power of x. All right, and a larger power of n is going to lead to a faster growth rate. Okay, this is kind of in the middle though, because we've got stuff that grows faster than x to the n, and we've got stuff that grows slower than x to the n as well. So something that was lower power, like a half for square root, we know that doesn't grow as fast as x to the fifth. Okay, and just bigger n means faster growth. So faster than any polynomial is an exponential, and it doesn't have to be e to the x. Anything bigger than 1 will grow faster than, so like 1.01 to the x will grow faster than x to the 99th. Eventually, it'll take a while. You'd really have to zoom out, but eventually 1.01 to the x is going to overtake any polynomial. Even x to the 999 or x to the 1 million, whatever power you want to put on there, I can outclass it just with 1.01 to the x. There are things faster than e to the x that we won't really need to worry about in this course. And of course, a larger base on an exponential will lead to faster growth. So 10 to the x grows faster than 3 to the x. I got distracted. I was answering some questions in the Google Meet. But there are things faster than e to the x, and one thing is factorial. Definitely grows really fast. We won't need to worry about factorial until much later in the course, and then we don't actually need to compare x factorial to e to the x or anything like that. Not that I remember. And then the fastest thing I can think of would be like x to the x or x to the x to the x or whatever, stuff like that. This is not going to be something that we're going to need to work with in this course. I may show you how to take the derivative of this later on, just because it's a really nice algebraic technique, and it's not on our AP exam, but there isn't much algebra on our AP exam this year. So it's really, I'm going to just show you these things for your own benefit. So we will definitely do implicit differentiation, where we're going to take the log of this thing, use log properties, and then take a derivative, and it's pretty cool. I like it, at least. Okay, something slower than a polynomial would be a log. So something like natural log of x. And let me think. The base is going to determine, I'm just trying to think if it's going to determine the growth rate inversely. Like if log base 10 would grow slower than log with base e. Let's see, it's the exponent we have to put on 10 to get a thing. It does seem like it. But I'm going to just quickly check on Wolfram Alpha and make sure. All right, so I realized I am not, I'm working off the document camera, so I can't really show you. But what I can do is grab a calculator and show you on my T83 Plus. I've got log base 10 of x and y1, so it'll graph that first, and then I've got log with base e of x and y2. And then we're going to watch them graph and see how it goes. So I'm going to zoom standard, and this is log base 10. It grows pretty slowly. And then log base e does grow faster. Okay, so it does, but you're not going to have to compare different based logs in this class. I'm just telling you, in case you were interested, the relationship there. Okay, so, lower base actually grows faster, which makes sense because, for a given number, like, say, 100, what exponent do I have to put on e to get 100? Probably something like 5 or 6 or something. What exponent I would have to put on 10 to get 100 is only 2. So it makes sense to me. And this is kind of like faster to slower. Okay, and within each of these, there are going to be, you know, determinations, but I'll let you work through that on the homework. And then the last thing I want to just warn you about before I move on is I'm going to say watch out for double asymptotes on
I'm about to turn my quiz. If I turn my quiz, can you tell me what the...
And pardon me, I didn't get to pause the recording quite in time. There was lively discussion of a difficult limit question. So, watch out for double horizontal asymptotes. On things that have, let me think about this. If it has e to the x and e to the negative x in both the numerator and the denominator, that is a chance for a double horizontal asymptote. That's really rare, though. So I'm going to say e to the x minus e to the negative x over 3e to the negative x plus e to the x, something like that. And maybe I'll change that to a 2 so I can actually run through this one and show you why there's two horizontal asymptotes. Okay. In this class, you definitely need to just know off the top of your head what the graph of e to the x and what the graph of e to the negative x both look like. It will just save you a lot of time and heartache and typing into Wolfram Alpha. Okay, e to the x, we know it grows. It's exponential, right? Just generally the shape, that's all I need you to know, right? It gets big. And then e to the negative x, it comes through and it decays, right? Which makes sense. E to the negative x at its core is equal to 1 over e to the x. Right, notice how I didn't say anything about negative powers here because all of a sudden, like, if we've got fraction, they would just kick over to the other side. And this is e to the x. As x goes to infinity, e to the negative x goes to 0. And I think that this is a big enough and important enough limit that I'm going to, like, put a cloud around it. Limit as x approaches infinity of e to the negative x is equal to the limit as x approaches infinity of 1 over e to the x, which is a bigger on bottom situation, meaning that it goes to 0. Okay. And we can see that, you know, just on my quick sketch, the bigger x gets over here, the closer we're getting to 0. Okay. This is a big limit here. This is going to come up repeatedly in this course. Okay, so if we want to find both horizontal asymptotes, we need to consider what happens at infinity and negative infinity separately. So I'm going to say, as x goes towards infinity, f of x is equaling, okay, as x goes to infinity, okay, well, e to the x and e to the x are the things that are going towards infinity. These are going to 0. Okay, so it's going to 2e to the x over e to the x, which is just 2. That's why we divide coefficients, because these things are basically 0 and as we go towards infinity. And so it's going to 2 over 1. Meanwhile, if we consider what happens as we go to negative infinity, well, this thing will go to 0 because we're going, this is like considering e to the negative x going towards infinity. We're going e to a negative large power is going to be very close to 0, right? Because it's going to be a big fraction with a huge denominator. So that's going to 0 minus e to the negative x is going to positive infinity. Same with this, so it's going to go to negative 1 over 3 when we divide coefficients, because this will also be 0. So negative 1 over 3. And again, I don't know if this is a good idea, but I'm just gonna try it. I'm gonna graph this thing. So it's an 83, so you gotta be judicious with your parentheses. 2e to the negative x minus, wait, no, positive x minus e to the next. That's the numerator divided by 3 e to the negative x plus e to the x. And let's just have a look at this, see what it looks like. Okay, we can see that it's going towards negative 1/3. That seems reasonable. It looks kind of like negative 1/3. We've got some weird activity. And then we are approaching 2 at the back end. I have a feeling there's more stuff going on here, although there's not going to be a vertical asymptote because I don't think this can ever equal 0. Yeah, because both of these things are always positive numbers. But I have a feeling there's a little bit more curvature to this if we were to zoom in. So maybe, I mean, I know this video is starting to get a little long, but let's just take the y scale. No. -4 to 4. All right, so it's coming along at negative 1/3, which it really does look like based on the scale of the graph, right? That looks like a third. No, it's just kind of doing an S thing. And we'll look at more S-shaped curves later. But I don't generally like trace, but just to kind of give you an idea of what's going on here, look at these y values. They're getting closer and closer to 2. Look at that. The farther I go, I'm just adding more. Closer, 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 but pretty slowly. Okay, so I need to, hold on, trace x equals 0, and then I'm going to go to the left, and you'll see that y is probably going to approach negative 0.33333333, right? Just like I was saying. Okay. So I'm not big on the numeric approach to limits, but I do like doing something like this, to where you can kind of visually see with the indicator what we're doing numerically, rather than looking at tables in this case. Don't much like that. Okay, another type of function that you need to be aware of that can cause a double horizontal asymptote is something like it's going to have a square root in it. And so what I'll say is, maybe something real plain. It needs to have something else in it so that you can't get algebra on it. But how about something like 4x squared plus 1, so that the square root is always existing, divided by, I don't know, x minus 2. Okay, now this is not going to be defined at x equals 2. There's going to be a vertical asymptote, and I can tell you about, and I'll probably use this one as a way to figure out, which infinities are we approaching. When I approach 2 from the right, that could be something I ask you. What is the limit as x approaches 2 from the right? And d and e would only be, half the answer, right? It doesn't exist because it's going to either positive infinity or negative infinity. I suspect positive if we go from the positive side, but I'll show you how to determine that. Okay, this causes a double horizontal asymptote really because of the square root of the x squared being not exactly x, right? It's the absolute value of x. So what we have to do when there's multiple horizontal asymptotes, just like I did up above, I'm going to consider both limits. The limit as x goes to infinity and its limit as x goes to negative infinity. So what we're going to do here is we're going to divide both sides by the same thing, or both top and bottom by the same thing. So we're going to multiply by a clever form of 1. I haven't done this for a while, so that's why I'm going to roll through this a little slowly. I'm going to say 1 over the square root of x squared. Okay. And then that's going to basically distribute to all of these, and so it's going to be 4 plus 1 over x squared in the denominator of the fraction inside that radical. And then I'm going to divide by 1 over x down here, because if you want to say that these aren't exactly the same and you need to put the absolute value around it, then you'll notice that both x and absolute value of x are positive, and so that go to a positive 1. I really talk to you about x divided by absolute value of x or absolute value of x divided by x. I will right after this, but and I'm going to say that this is, so I'm not going to make this a 2-hour video. This is going to be 4 plus 1 over x squared, the type of thing that when x goes to infinity will go to 0, divided by, okay, so what this is going to be x divided by x is 1 minus 2 over x. And maybe you're still like, wait a second, this isn't the same. You need to have that absolute value there. And you'd be right. So maybe 2 over the absolute value of x. Either way, as x goes to infinity, this fraction is going to 0. So I'm going to 4 plus 0 over 1 minus 0. Okay, so that limit is going to square root of 4 over 1, so that's 2. Okay, eventually you'll just be able to look at it and be like, wait a second, I know this is a double asymptote situation, so I know it's square root of 4 over 1, because exponents are essentially the same, because it's the square root of x squared, kind of like x. If this had been 5, it would have been 2/5, right? As x goes to negative infinity, and this is where I'm kind of forgetting how you can show it in the algebra. Oh, yeah. So this one I'm going to have to pause and then come back to, but I'm going to do the same exact thing, right? Yeah. Okay. So this was not entirely true. It was x divided by absolute value of x, which when x is positive will always be 1, right? Because absolute value of x is the same as x when x is positive. Okay. So really, this went to 1 minus 0 is really how that went. And then I'll do the exact same thing. So after this algebraic manipulation, it's going to look like 4 plus 1 over x squared divided by x divided by absolute value x minus 2 over absolute value of x. These are going to 0. Those are just big zeros. And then, but as x goes to negative infinity, I've got negative numbers, right? And x and absolute value of x have the same size. So if I take x and I divide it by, and x is a negative number, but I divide by its positive version, I'm going to get negative 1. So I have square root of 4 divided by negative 1. And so that's going to negative 2. And that's why we see a double horizontal asymptote situation. Is because, and you can also see it up here. Guarantee this is going to be positive, right? Because you take a number, you square it, it's positive. You multiply it by 4, it's even more positive. You add 1. This is a very positive number. And then we take the square root. This means the positive square root. It's not the solutions to that thing squared equals whatever. We're taking the positive square root. And so we'll get a positive number. This, provided that x is positive, will definitely be positive. Positive enough, going towards positive infinity, very positive and bigger than 2. And if it's negative, well, then this will certainly be negative, and the denominator will be negative. So we've got positive divided by negative, so this has to be a negative number. It can't be positive. So I think that's what I have to say about that. And then more generally, we do need to be very aware of this this function. And since I've just call it h of x equals, and I guess you could say that this has a double horizontal asymptote. I mean, it's kind of not the most interesting, but it's a good example of a function with a jump discontinuity. Okay, so let's start thinking about it. I already said that when x is positive, x and absolute value of x are the same thing, so this fraction would come back 1. So it's constantly 1. And then when x is negative, well, this will be the positive version, and that will be the negative version, and divide them, and you'll have negative 1. Whoops. At 0, hopefully in pre-cal, they told you that 0 over 0 is not a real number. It's not equal to 1. It's not equal to 0. It's not equal to anything. So this is undefined at x equals 0. So we have little holes here. But otherwise, that's what the graph of that looks like. Okay, and we'll have a lot more to say about this, but you need to know the shape of that graph, because I might ask you for the limit from the right or the limit from the left, or does the limit exist? Stuff like that. And then it can also help us in situations like these. Algebraic manipulations for limits are not really a focus. I think I would be perfectly happy for you to say that the horizontal asymptotes of this were 2 and negative 2 just by inspection, just looking at it. But I'm going to explain to you in this video why it is the way it is. All right, the last situation I wanted to talk to you about is when the limit equals infinity. Okay, and I think I do need to just mention that this means that if we say that the limit as x goes to infinity, as x approaches c of f of x is equal to infinity, means that, means that we can make the values of f of x as large as we want, right? F of x can't equal infinity ever, but the limit, we say it equals infinity. If we can make f as large as we want by just choosing values of x sufficiently close to c, like, if you think about a double vertical asymptote both going up or something, you can make that as large as you want. I think I've mentioned that at the beginning of this video. Okay, so that's when the limit equals infinity. And we can also say that it equals negative infinity if we can make it as large of a negative number as we want by choosing values of x sufficiently close to the point we're interested in. So what I'm interested in is going back to that function that I was talking about with the double horizontal asymptote. G of x equals the square root of 4x squared plus 1 divided by x minus 2. Okay, you know that there's going to be a major problem at x equals 2 because of division by 0. What we'll find out more later in investigation of limits is 0 over 0 we can do something with. Okay, and you may have learned that in pre-cal. There's usually a hole or some other thing going on. Number divided by 0, though, if I plug in 2, I'm going to get 16 square root of 17 over 0. That's a major problem. There's no fixing that. That's going to be a vertical asymptote. Okay, but what if I was to ask you the limit as x approached 2 from the positive side of g of x? I'd say, is this limit equal to positive infinity, negative infinity, or neither? Explain. Okay, so you're not going to just be able to say d and e. Okay, that's not going to be an option in this class. In general, there's not just some easy way out in this class. I'm going to just ask you for more. And if you're looking for an easy way out, you might as well just, not. So, or just skip the problem. Move on to something that you deem worth your time. So this is going to be what happens as I get closer and closer to 2 from the positive side. So I'm plugging in 2.1 minus 2. That's a positive number. 2.01 minus 2, still a positive number, 2.001. Okay, no matter what I choose, if it's bigger than 2, this denominator will be positive. The numerator is always positive, so I know that this limit is positive infinity because it's positive over positive. Now, as x approaches 2 from the negative side, like say 1.5, 1.8, 1.9, 1.99, 1.999, 1.99999, this is always going to be a small negative number. So when I take the limit of g of x as x approaches 2 from the negative side, well, that's going towards a positive over a negative, which is going towards negative infinity, right? Because of its vertical asymptote, and you can't see that, there's just a negative infinity there. Okay, I think I should point out to you just a couple of other examples that I think are worth mentioning in this video. And it's the very end. I'm over half an hour in, so if you've watched this far, you deserve a little something. So I'm going to point out a couple that I know that people have had problems with in the past. That one, and some kind of like composite limit. Limit as x approaches infinity of, just a second. Oh, yeah. Something like cosine of something complicated. Okay. This one, it kind of depends on you knowing the graph of natural log, which I do expect that you will. If you don't yet, I need you to just kind of like e to the x and e to the negative x. I need you to have just like a general picture in your mind. Okay, as we approach 0 from the positive side, natural log is going to negative infinity. And if we think about that, what exponent do I have to put on e to get 0? Well, I would have to put a really, really negative exponent on e to get close to 0. I can never actually equal 0. That's why we say the limit is negative infinity. Okay, because log of 0 is undefined. But that's one that you can tell from the graph, and you can also think about what it means to be a log. What special exponent do I put on e to get towards 0? Well, that would be a really large negative number. Okay, and then over here, what we can do is that because this, and again, this is beyond what we do here, but I'm going to point out that since cosine is a continuous function, we can pass this limit through to the inside and consider what's happening to the limit of this. Okay, well, we know that since this is heavier on bottom, this is going to 0. So this is equal to cosine of 0, which is equal to 1. Okay, that's something that, that's definitely the type of problem we could see here. Oh, and I realized that there's one more thing. If I'm talking about limits as they go to infinity, I do need to mention this. And I, in the past, have not really included this as part of my AP Calculus course because I didn't think it was really necessary. But I did see this spring a way that we could test you on this. And I do believe that technically you are supposed to know this, but and that's the definition of the number e. E, we know it's, you know, what I always say about it is it's a number, it's between 2 and 3, and it's not anything to be scared of. Okay? But I'm going to actually define this as the limit as n goes to infinity of 1 plus 1 over n to the nth power. And I'm not going to prove this for you, I'm just going to, actually this is not something, it's a definition. Okay. It's also possible to consider, some people would call this 1 plus p to the 1 over p power as p approaches 0 from the positive side, I believe. It really goes back to the kind of the compound interest definition of E and the different ways that we can see it with population growth. I can see all the different ways that it fits in. But that will be something that we will use maybe at some point really much later in the course. But this is not super important. But again, something I figured I'd just mention at the end of the video. So that's all I got for you.